So yeah, thank you for attending this organized session on coupling economic and ecosystem and water models for local global sustainability analysis. My name is Juris Baldos. I'm from Purdue University. And today we are going to have two presentations. The first presentation, I'll be presenting that, and it's about integrated economic and ecosystem modeling. Um, and then after the presentation, we'll have a discussion, around 10 minutes. And then we are going to go to the next presenter on environmental stressors can intensify the impacts of pandemics on Earth's natural resources and food and global systems, presented by Marzie Bahalu from West Virginia University. So for the attendees, I guess we just need to make sure that everybody's muted. And then for the presenters, if you're having trouble in terms of your internet connection, you could turn off the videos. And yeah, if you have questions about the presentations or comments, you could just easily type it in the chat box. That way, we'll be able to record what's the questions, and when we post it online, people could view it. All right, so let me start sharing my presentation. Already, let me start full screen. Can you see my presentation?
Yes.
Okay. So I'm going to start. So yes, the title of my presentation would be Integrated Economic and Ecosystem Service Modeling. And this is work in collaboration with University of Minnesota and also World Bank. So just to quickly motivate this presentation, here's work by the World Economic Forum, and I think this is an accounting firm, PwC. And what they did is they tried to measure how nature is, or how the global economy is dependent on nature. And they did like expert opinion on which sectors are highly dependent on ecosystem services and biodiversity. And what they found is like, at least for year 2019, almost half of the world's GDP depends on biodiversity and ecosystem services. And they rank that dependency depending if it's low dependency, medium dependency, and high dependency. And as you can see here, the dependency will vary depending on which country you are. The higher dependency will be mainly on the developing regions like India and Indonesia. But of course, US and EU are also reliant on these services. So in terms of the literature, the analysis on relating economic and environmental modeling, they're limited to country-level analysis, and there are some global evidence. So for example, for country-level analysis, you have this work by Banerjee et al., and they use this country CGE model and link that to an environmental model. And they examined Guatemala's environmental economic accounts, and they tried to apply that in the analysis of the forestry and wood sector and try to connect it to health outcomes. And then there are also global level studies. One application with the GTAP model is by Bauer and Wang. They focus only on one ecosystem service, which is pollination, and they assume that the collapse of pollination would result in welfare losses of around 127 to 152 billion. And then there's this big report by Waldron et al., which essentially tried to conduct a back of the envelope calculation on what would be the gains or losses when we protect 30% of the planet. And they found that they are able to calculate like a marginal value for protecting the environment that could range around 1.7 to 170 to 530 billion. And then there's recent work by Johnson et al. With WWF, and they use the GTAP and INVEST model to do the soft coupling. and analyzed the different implications of income and representative concentration pathways, and how would that affect the BES, which in turn, how would that affect my economy? And they found that under business as usual, the global GDP would fall by around 479 billion. So the main goal of this work that I'm presenting is just to provide additional evidence on the global economic impacts of loss of biodiversity and ecosystem services within the CGE framework. And we try to improve on the existing framework by doing this two-step approach on coupling the GTAP model and the index model. So the CGE model that we're using here is the GTAP AEZ model. So it's different from the standard GTAP AEZ model because it allows heterogeneity on the land endowments. So if you're familiar with the standard model, rather than just having land as an input, now we have land and it's classified according to agroecological zones. And then there are also capacity for land transformation across uses. You could use land for forestry, cropland, and pasture land. And then you also have this capacity to increase yields by substituting between input land inputs and non-land inputs or intensive and extensive margins. And then for this particular application, we are using this GTAP V10 land use land cover database aggregated to 37 regions and 57 sectors. And here's just a quick picture of the GTAP agroecological zone. So essentially, it classifies each grid cell according to length of growing period and the climatic region, boreal, temperate, and tropical. One improvement that we made here is we allow this capacity to have a land supply within the AEZ and region, and this is based on this land supply of function by the magnet model. So we just adopted their approach. And this is particularly useful if you want to shift land supply, if you're implementing a preservation of biodiversity, for example, or forestry, you could do that within this framework. And this is just one of my co-authors calculated essentially the potential for cropland that you could use. And this potential is based on what type of soil, the topography, the land use adjacency, if it's close to another cropland, and cultivation constraints, whether it's low salinity and if crops can actually grow in that part of the world. And we aggregate those information in order to inform the land supply function that we impose in the GTAP model. So as I've mentioned, we're also using this INVEST model, this integrated valuation, ecosystem, and services and trade-off models. So this was established with a partnership of WWF, the Nature Conservancy, Stanford University, University of Minnesota, and the Chinese Academy of Sciences. So INVEST it's an open source tool, and so it estimates around 20 types of ecosystem services. Most of the inputs that is used by the model will be land cover, but there are other ecosystem services that use other inputs. And then the cool thing about the INVEST model is it's spatially explicit, it's high resolution, and it's also widely used. So it's not just used within the US, but also in China and in Europe. And there are a lot of applications with this model. Okay. So in terms of the methodology that we're using here, we're using this maybe two-step coupling approach. So what I mean by this approach is we first generate the baseline, do a forward-looking projection with the GTAP AEZ model, just growing population and so on. And that would generate land cover maps by AEZ and by region. And those information are then downscaled via this spatial economic allocation landscape simulator or SEALS model, so that it would be in a fine scale resolution. I think it's around, I can't remember, it's around 30 meters or so on. And the reason for downscaling is that, remember, the INVEST model used land cover maps, and you need to have a downscaled land cover so that you can have the investors can calculate the changes in ecosystem services. So once we have that land use map that's downscaled, Invest will then churn some outputs in terms of ecosystem services, for example, pollination, and then we re-aggregate the changes in pollination and then plug that into the GTAP model to generate a new baseline with this BES impacts. And this is how we quantify the contribution of biodiversity and ecosystem services in the economy. So in terms of the biodiversity and ecosystem services that we are covering here, we're only focused on 4. So we have pollination, and that's going to be dependent on the grid cells in a region, which is considered as a habitat of pollinators. So if you expand cropland, you'll have less habitat for pollinators, and that would in turn reduce pollination services. And the way we incorporate that in the GTAP model is via changes in crop productivity. So you also have marine provision here. So I think this doesn't require on the land. This doesn't require land use maps, but I think assumption on population and so on. So this is a separate model. But the idea of the fish provision is that if you have increased rates of catch, then you'll have less fish to catch in the future. So the fishery sector productivity will go down, and that's how we apply this in the GTAP model. And then you also have like timber provision, and it depends on the amount of forest land that's available. So this is tied to the land cover maps again that we're generating. And the assumption that we're doing here is that if you have an increase in timber carbon storage content, that would translate in terms of increase in timber sector productivity. And then finally, there is this climate effect that we're calculating, but this is calculated ex post. In a way, this measures the avoided damages from climate change. If we increase carbon storage, that would reduce carbon emissions in the atmosphere, and that could lead to changes in the social cost of carbon. So it's a proxy for the effect of climate change. And then this is just a validation. So we tried to compare the global changes in land cover with the GTAP AEZ model with the AIMs. And in general, we are within the range. So we did, I think, forward-looking projection 2014 to 2030. So we're a bit confident that, yeah, at the global level, we could actually capture whatever the AIM groups are projecting in terms of future expansion in cropland, pasture, and forestry. Now, in terms of the inputs, again, this is how we are using it. So we have an updated baseline. So we updated baseline from 2014 to 2020. We take population change, real GDP change, changes in capital and labor from the Econ and Map database. And we have sector-specific productivity shocks from Ludena et al. So this is for livestock and crops. And then we had an assumption on the forestry sector productivity too. And I think we calibrated based on agricultural PFP growth. And then for the set of results that I'm going to present today, I'm going to focus on 3 scenarios. So baseline for 2021 to 2030. So this is without the impact of ecosystem services. The other scenario would be business as usual. So this is a scenario with the impact in ecosystem services. So this is like the 4th step, the full circle of the picture that I showed you. And then finally, we have this BAU with rigidities. So business as usual rigidities. So essentially, when we mean about rigidities, we reduce the value of certain economic parameters within the GTAP model, particularly in the land use transformation, how easy it is to move land across uses, and also input substitution parameters. So here are some key results. So what we're looking at is we're looking at change in GDP under the BAU relative to the baseline. And then we've aggregated the results according to low income, middle income, upper middle income, high income, and global. And what we found is that at the global level, the change in real GDP in 2030 would be falling by around 90 billion compared to the baseline scenario wherein the ecosystem services are ignored. So under the business as usual, this 90 billion would be the reduction in GDP when you have less ecosystem services in the future, given the business as usual trends in the population growth, demand for food, and so on. And then if you further add climate damages, so this is ex post calculation after the simulation, the loss on ecosystem services would be around 225 billion. It's the cost of the global economy. It's a really large component. And then in terms of the share, in terms of the share of global population that are affected, who's winning, who's losing, who's experiencing a welfare loss, we generally see that most of the fraction of the population will be experiencing loss in GDP when we have this comparison between baseline and BAU. And then there are also losses on economic welfare. So these are the fraction of population in the world who will experience these losses. And these are just the regional outcomes based on the change in the comparison and change in GDP between baseline scenario, so scenario without the ecosystem services, and the BAU scenario with ecosystem services. And we see that most of the countries in this corner here are the ones who are generally affected by this change in ecosystem services over this forward-looking projection. We have Bangladesh, Madagascar, Egypt, rest of Southeast Asia, Indonesia, and Malaysia. And these are generally regions which are dependent on either fisheries or forestry. But there are also other regions, surprisingly, like Angola, DRC, they experience an increase in GDP over this period. But yeah, we need to look into that further. Okay, so that's the quick comparison between GDP under BAU and the baseline. Now let's try to switch gears and look into and compare the results with and without the rigidities. So here, I think this is the original graph that I showed you a couple of slides ago. So this would be the comparison of BAU relative to baseline. Now here is this BAU with rigidities relative to the baseline. And as you can see here, the change in real GDP is much larger. So here the range is around negative 200. This is around negative 100, 400, 1,400. So in general, the results of the model that we are looking at here would be sensitive to the assumption on the economic parameters. So given that we really need to account for some sort of sensitivity analysis, maybe a Monte Carlo type of analysis, so that we could quantify the impact of economic uncertainty in the economic parameters on the results that we're generating here. And then in terms of absolute dollars, the upper middle income countries are the ones who are experiencing this huge reduction on GDP under a more rigid economy. And this is just a quick comparison across all regions. So we're comparing here results of BAU with rigidities relative to BAU. And we're looking at change in 2021 to 2030 GDP in percent. And as you can see here, there are some regions that switch places. For example, now rest of Southeast Asia is the one who's experiencing this huge loss in terms of GDP change. China also experienced that loss. But there are also some regions which still remain the same, like in the region which lose a lot. So Bangladesh, Egypt, Indonesia, and also Malaysia. And just to quickly summarize what I've presented. So what we presented here is a state-of-the-art modeling work. So coupling two models. The GTAP model is widely used as an economic model for analysis of trade and other policies. And we're coupling that with this ecosystem service model, the INVEST model, which is also a well-known environmental ecosystem service model. And this is something new, and this is something that I think is ripe for future research. And then from what we've seen in the initial results that I showed you, we see that global real GDP declines by around 90 billion. So if you think about the results that I showed you a while ago in terms of the literature, it's a little bit smaller compared to what they assume, mainly because we're assuming a more, I guess, lesser change in terms of the biodiversity and ecosystem services, because we're assuming BAU. The other global studies assume a complete collapse, for example, of pollinators, or a larger BAU scenario wherein you have high consumption and so on. And then another reason for a relatively low change in relatively low estimate of the loss would be we're only looking at a subset of ecosystem services. So we're just looking at 4. Maybe in the future, we're going to extend that work to look at other ecosystem services and see how we could incorporate that in the GTAP model. And then when you incorporate the climate damages, the cost actually goes up by a lot, so from 90 to 225 billion global reduction in GDP. And now, as I've mentioned, this is just a limited set of ecosystem services. In the future, we're going to look into other ecosystem services that INVEST model is turning out. And maybe we should also take a look into other scenario assumptions which are more extreme in terms of population growth, trends in food consumption, and so on. And there's a lot of work to be done, and hope that in the future we'll have more presentations here, maybe in the next GTAP conference. So I think that's the last part of my slide. Thanks for listening. I guess we could open the floor for questions. So if you have questions, you could type on the box so that we could record your questions. Let me share my screen. We can see if there are some questions in the chat box. So far, there are no questions.
Yes, I have one question. Can I just ask it? So what will be the implication for the GTAP community in terms of connecting with other disciplines, and what are the lessons learned here in your communication with the INVEST people?
Yeah, so there are a lot of lessons. Some are related to the modeling, and some are related to how we communicate the results. I think that's kind of the one particular lesson that I've learned, especially when we're talking about when presenting this work to people who are really involved in biodiversity and ecosystem services. Some of them are a little bit looking at the numbers, and they see that, hey, that's a little bit small, but like 90 billion, for example. So what they tend to do is they tend to go to the extreme, which is what I showed you in the initial picture, wherein we have this half of the world's GDP is dependent on this ecosystem services. So the idea, I guess, would be to how to communicate properly that, hey, we're just focusing on a limited set of assumptions. And then with an economic model, there's a capacity to substitute and to mitigate whatever reduction in ecosystem services we have by using other inputs and so on. So that's one lesson, I guess, in how to communicate properly. And then another lesson would be, especially in the GTAP front, we don't have a robust modeling system in terms of the provision of ecosystem services. So ideally, what you want is you want to have, for example, for pollinators, you want to have an explicit input in terms of the pollinators that could be related to the cover of natural land. So right now, so in the current work that we're doing, everything is just a shift in productivity, at AO shock, a TFP shock. But maybe in the future, we should focus on explicitly incorporating the input of pollinators, putting a value on that, and then explicitly modeling that within the production framework and see how would that this new modeling framework, how would that change the way we do things. But yeah, it's really it's nice to work with these groups, because it's really something that we haven't done in terms of the GTAP community, or also in the CG modeling community. And I think there's a lot of opportunities here to collaborate with them and to publish exciting work. Yeah. Thanks, Iman, for the question. Any
Maybe
other?
I can.
Oh, sure. Oh,
Yeah, maybe I can ask a question.
Sure.
Boris, thanks a lot for the great talk and very interesting, inspiring work. Have you thought about tipping points in your analysis?
Oh, yeah, no. That's a good question. Thanks for asking that question. So in the process of the project, we did like the tipping points. So the main problem is when we plug that into the CGE model, because for tipping points, there are these huge changes in, like, full collapse, or there's no production, or there's no crop line in a particular area. The problem is when we do the numerical solution, a lot of the times the GTAP model doesn't solve. So this makes me think that there may be other uh, types of economic modeling that we should use in order to fully capture this, these tipping points. So this has been a source of frustration in my part, and also in the part of the ecosystems modeler, because we can't really model we can't capture the extreme case that they're generating in their ecosystem model, because we're limited with this constant elasticity of substitution framework. You can't have like a zero production in a particular region. So that's something that we faced when we're trying to incorporate this tipping point.
Yeah, I'm not surprised that it's not a straightforward thing to implement, but maybe when talking about tipping points, maybe also another follow-up question would be, do you assume a linear change in pollination services with respect to the land use changes, or do you like, is this a logarithmic or like other functional relationship? Because
so I think sure. So I think so what we do, so this is the pollination side is generated by the invest model. So my assumption there is that it's not linear, because you're going to have depending on how the spatial allocation tool allocates the land cover generated by GTAP, it's going to be different. But yeah, I think it's going to be nonlinear. I'm not directly familiar with the invest model, but my hunch is it's going to be nonlinear.
Okay, thanks. Thank you.
Thank you. Let me see. 5 more minutes for discussion. Anybody has a question? So if there are no questions, Iman, should we proceed to the next presenter, do you think, or should we wait a little bit?
I think so. Let's move on. So
Okay.
I don't see Marzia here, but I have this slide, so we can wait a little bit, or I can.
Okay. So let's try to be on schedule then. So for people who want to take a quick break, maybe we'll take a quick break. So we're gonna start we'll follow the schedule, and we'll start at I think 9:05 ETD time. Maybe that's a good idea.
Okay, so I will start sharing and keep the title slide up. So.
Yeah, that would be great. Thanks, Iman. So yeah, we'll start in 5 minutes. So Iman, did you wake up at 5 today?
Oh my God. So yesterday, I was in European area and it was on building time. So I had a presentation, just this presentation, I did it yesterday too. So I did a bit different. And my presentation was at 4 a.m. So I woke up.
Oh my gosh.
It was fun, yeah.
Yeah. I'm sure you had lots of coffee to do that. So it's like what Ala is doing, because Ala is like what is that? Pacific time, so it's like 3. I
Yeah,
guess, or 2 in the morning.
3 hours.
Oh,
yeah, 3 hours.
yeah. So what paper did you present? Is it the
So the pandemic one, yeah, the current presentation, but with more focus on policy. So it was a policy session, and they wanted to have something about resilience policy, how to get prepared if we have these kind of compound extremes. So, yeah,
that's good.
Yeah, it's interesting. It was a policy session, but there was no policy maker. It was more people from policy interests. So,
yeah.
Having this conversation, first of all, between the scientists and economists first, they resolve the issues between themselves and then move forward. How about you? Have you hosting any session yesterday? No.
Yeah, I hosted like a session yesterday with Jing on the water, and also I think there's a session on health in Europe. And then tomorrow I'll be helping on a session at 5 a.m. too, and also presenting with this work with the CGAR group on the TFP. And yeah, the contribution of CGAR on the agricultural productivity and the application with the simple model. Okay, it's an exciting week. All right. Yeah. Where are we in the schedule? Yeah, 2 more minutes.
Yeah, I really enjoyed the discussion. Yesterday we had a very, very active audience. Started to challenge us.
Oh, that's good. Yeah, in Jing's session, the discussant was wonderful because he really summarized the key point of the presentation and also like did some recommendation, which is something maybe in the economics, when you attend the economic conferences, you could have that. But I think for the AEA, usually you don't have that kind of comment. No. 9:04, 1 minute.
Okay, it's 9:05. Should I start?
Yeah, you should start. Yeah. So we're going to be on time. Okay, man, thanks.
Thank you very much for giving me the opportunity to present this work. My name is Iman Haqiqi. I'm a postdoc at Purdue University. And this work is a collaborative work. I like to give credit to my co-authors. So Daniel Grogan is research scientist at University of New Hampshire. She is responsible for the water balance model simulations and the hydrology part of this project. Marzia Bahalo is a PhD student at West Virginia University. We started the idea together, and it was the start of brainstorm. We'll talk about that. Juris Baldos contribute to this project in updating the database to 2017 for Simple G, and then he contributed to the food security module of this one. Tom Hertel and Jing Liu also contributed. They are, so Tom Hertel is distinguished professor at the Department of Agricultural Economics, Purdue University. Jing Liu is a research economist at the same department, and Juris Baldos is research assistant professor at the same department. Tom and Jing also contributed to ideas, comments, and in improving the simulations. So this is a very ambitious project. And by ambitious, I mean we are trying to connect a gridded economic model to a gridded hydrologic model. So by gridded, what I mean, if you consider the world and divide that to different grids also, you see they're a little bit different in size, but in 5 arc minutes, the world will be around 10 million grid cells. Out of that, around 2 million has cultivations on it. So the model that we are working on this project has around 2 million grid cells with cultivation, which means crop production or livestock production, and it is connected to irrigation, a hydrologic model. So the idea of this project started before COVID. And we were working on this paper. It was presented at AAEA. It's a poster. And we were thinking about the impacts of these cyclical changes in economic growth and the cyclical changes in groundwater recharge. And we were thinking about if they are kind of in opposite directions, when the demand for water is high, but the supply of water is low, then we will see depletion in groundwater. And that means stress on groundwater. And then we prepared the presentation, and when we were presenting this, the COVID happens, and we saw a great potential here to connect changes in the economy. In lockdown, you have decline in income, decline in economic activity, to changes in water resources and land resources around the world. And going back to what has been done so far in the center and around the world, there are a lot of studies trying to investigate the impact of changes in income and population on food security, sustainability, and different outcomes of that. There are a lot of studies looking on extreme events that can have impact on food security and sustainability. The point is that, so let's look at these 2 figures. This is interesting. So at the beginning of the pandemic, we saw that for China's lockdown, economic activities were very small, and you see a little bit better or cleaner air over China. And people started thinking about the possible impact, positive impacts of COVID-19. So we asked this question. Obviously, we don't know when a pandemic will happen or when an extreme event can occur, or when they will be combined together. So, but the interesting question will be, what if in the future we have a situation that a pandemic is combined with widespread environmental stress, means drought or heat stress? That's the question we want to answer here. So for those people who are not so patient, I just have a summary of the findings in this slide. So what you see, we find that we had very specific scenario of pandemic, very close to COVID-19, and very specific scenario of drought and heat stress. In our specific scenario, we found that a pandemic like COVID-19 could reduce emission and stress on water and land by up to 5% around the world. But when you combine that with heat stress and water stress, and that's the specific example I will show you, you will see that you observe increase in groundwater withdrawal, cropland extension, nitrogen fertilizer application, around 2.5% in this exercise. But also the number of food insecure people by around 150 million additional people. So this is very important. Both sustainability and food security are affected. There are different differences across regions that depends on the scenario that we are looking at. For this study, here I'm showing all the studies that have been done connecting water balance model and simple G. It's in 2017, and they were talking about sustainability and the trend in water resources. What happens if you have some sustainable irrigation? What will happen on food security? We will build on this. We improve the simple G model, we improve the connections, and we improve the resolution. Also, we will consider previous works on heat stress and the impacts of extreme heat stress on crop yields. We will have an improved version, and we'll talk about that, how we'll model this. And then for the potential impact of COVID-19 or any other pandemic in the future, we consider change in income, which affects the consumption of food, and change in productivity. We had another paper published that calculated this. So the productivity of people who are working in food industry, or they're working on packaging, transportation, and other things. So going to methods. So I like to start with introduction to GLASS. So GLASS is Global to Local Analysis of System Sustainability. It's an approach, it's framework. Also, it's the name of a network that consists of different people from different disciplines. We talk about climate, water, land, and different aspects of sustainability and food security. But the most important idea and point here is that we should consider the impact of global drivers to local issues, as well as the response of local decisions and local, for example, crop production or land use and water use and policies and shocks. The feedback from local to global will be significant too. So it's not only the impact of population and the income growth on water resources and land, but also if you have local policies on groundwater, for example, sustainability, it will have implications for global food security and other locations of the world. For this project, we have three different modules. So water balance model is a hydrologic model. In terms of economics, we call it the high resolution for 5 arc minute, but for hydrologists, they call it macro model because they were working on very high resolution models. So it's a very complex model. It takes weather information and some exogenous decision factors like the extent of irrigation and irrigation technology, and produces the output regarding the groundwater level, surface water availability, and evapotranspiration. So those will be fed into simple G, and will affect groundwater supply, surface water supply. And for evapotranspiration, we will consider changes in agronomic water demand. So we have economic water demand and we have agronomic water requirements. Also, the evapotranspiration is used to simulate the yield gaps. Simple G will solve these shocks at the grid cell level. So each grid cell will have different variables and decisions in crop production, land use, water use, non-land inputs. And then we will see at the end, having all the markets interacting, what will be the irrigation extent at each grid cell and what will be the irrigation technology. So the irrigation extent will be feeding back into WBM. So, and then the irrigation technology will be transferred to irrigation efficiency. So this is how we connect these two. And for yield shocks, it's worth mentioning that Simple G has only one aggregated crop. And by that, consider it as a GDP index for crop production. It's a combination of different crops, but it's an index. Agronomic models usually have crop by crop yield estimation, but for this we have to calibrate our emulator. So GCWM is global crop water model to use the information from WBM and convert it to yields for aggregated irrigated crop and aggregated rainfall. If you are interested in a water balance model, I can talk about this later after this talk. But in brief, water balance model considers the interaction of weather, agricultural practices, soil, groundwater, and how they will affect each other. Simple G, on the other hand, if I want to talk about this briefly, we have food security and we have sustainability. Food security is measured at national level or regional level, but sustainability is measured at grid cell level. 5 arc minute is around 10 kilometer by 10 kilometer almost at the equator. So Simple G takes the information regarding income, population, and investment for demand for bioenergy, and takes the gridded information on land, water, agricultural production. At the equilibrium, it will determine the prices, land use, and water use at different scales. This is, I don't know if that's clear enough or not, a very simplified version of the main part of the model. So at each grid cell, we have, starting from bottom, cropland, and we have a transformation elasticity. It's a quantity preserving CET that allocates land to irrigated land and rain-fed land. And then for irrigated land to the left of the tree, so you have different sources of water, like groundwater and surface water. There's a substitution there. There's a substitution between volume of water and equipment, and then substitution between water and land, substitution between the composite of water and land, and other inputs. So this is the nested CES structure. We assume national markets for crops and fertilizer, but grid cell level markets for land and water. So this is a very complex and huge model. In terms of equation, probably this is the main equation at the grid cell level, but it is simple. It considers the main variables and equations important for agriculture, or agricultural production, food security, and sustainability. You can look at the simple papers by Joris Paulus and Tom Rutter. Okay, what are the shocks that I'm going to show you here? The specific scenario that I talk about it is this one. So we have income shocks, which is based on World Bank estimates. These are the GDP lost because of COVID-19. And then we have water stress shock. It's not a widespread water stress. It's not a drought. It's based on 2015 and 2016 observed changes. So what we wanted to do, we wanted to be realistic because biophysical systems are somehow act differently. We cannot have a uniform water stress for all around the world. Sometimes if you have water shock drought in one place of the world, there will be water abundance in other parts. Also the same for heat stress. So this is for 2015 and 2016. And putting it into the emulator, we have the impact of heat stress on crop yields for rainfall agriculture. So basically what we want to say is that imagine that COVID-19 happened in 2015 and 2016. Combine the income shock, the water shock, and heat stress. What we'll see. I told you about the overall result. These are aggregated to regions. The way to read this, we decompose the impacts of productivity from pandemic, water stress and heat stress, and income reduction from pandemic. And in general, you can see, for example, looking at sub-Saharan Africa, the heat stress impact is red, and the impact on hunger is dominant from heat stress. There is a negative impact on hunger. That means it increases hunger in the number of people. Let me, sorry, I missed this. Let me introduce this metrics here. For sustainability metrics, we have greenhouse gas emissions. For water, we consider groundwater withdrawal. For land, we mean cropland area. For hunger, we calculated the population under minimum caloric requirements. And food prices is the average of all food prices. Okay, now it's more clear here. So looking back at sub-Saharan Africa, so pandemic and environmental stress together will reduce greenhouse gas emission. Okay. But on the other hand, they will increase hunger, and that's bad news. The same for China. China is different in terms of income because in 2020, the impact on income for China was positive. But again, heat stress and productivity shock from COVID, they contribute to increase hunger in China. So the whole idea of this, we are not predicting anything. We don't want to have some prediction and estimation regarding future situation. But what we want to say is that this framework is able to show you the hottest spots that are vulnerable to in terms of food security or sustainability. We can have the results at grid cell level for sustainability, and for food security, we can have it at regional. Moving forward quickly, I just want to show this. This is very important. If you want to have a resilience policy, we need to have some flexibility in the system to be prepared. So I want to show this. The simple G model has a specific Armington structure. So at regional level, we have a substitution, a perfect substitution between global production of crops and regional production of crops. And each region also has an Armington type specification. So for example, if we have within the US, for example, or within South Africa, we have different regions. There is a substitution between crops that are coming out of each sub-region. And also there is another substitution among grid cells. So they are not exactly perfectly substitutable, the outputs of each grid cell. So what I did an exercise here, and in the model we have some positive numbers for these parameters. What I did, I just reduced them to show little flexibility or more flexibility. So why we are doing this? We want to show the importance of international trade and domestic trade. If the W is high, that means you are flexible in terms of trade. You can have alternative sources of food. But if all of these parameters are small, that means you don't have so much flexibility moving, changing the sources of food. Here is changing W1, just having that top-level Armington structure. Just lowering that, you see, will increase the impact on prices. If you have more flexible international trade, the impact on prices and crop production will be lower. Look at North Africa, for example, from 50% to 40%. That means 10%. You can reduce that 10% just by having a better international trade. And this one is the second Armington layer. You can even reduce that price shock from 40 to around 10% by having a better trade within a country or sub-region. So it's a little bit, it's not as straightforward, because when we have aggregate region, sub-region might be countries, but anyway, so trade within a country is very important. Imagine that you have stocks in part of the country, you have better production in one part of the country, you can move it to other parts. And then finally, if you have different options and alternatives within production technology, within a grid cell, for example, rain-fed to irrigation or vice versa, or having flexibility to apply more nitrogen or less, or using more labor and capital. So these are the flexibilities that exist. And if you have those flexibilities, you can reduce the impact on food prices, and we can improve food security. Concluding with this one, finally, if you have lower food loss and waste, just you know, in Europe and advanced countries, 30% of food is wasted by consumers. In developing countries, around 20% is lost after production. So imagine that we reduce that loss and waste by 25%. And it is not unrealistic. In the COVID era, you have seen that people trying to save food at home, you know, going less to restaurants and, you know, reducing the waste from restaurants and others. So it is not unrealistic, but anyway, just I want to show this. And the green and blue colors showing the impacts of the lower food loss and waste. And you see all of the metrics are going to decline. That means positive impact on sustainability, lower land use, lower water use, lower GHG emissions, and also lower hunger and lower food prices. So this is very critical. And I know it is difficult to do this, but this work shows that in a time that you have a compound events like heat stress, drought, plus a COVID-19 or COVID-25, I don't know, then lowering food loss and food waste around the world can help reducing the stress on water resources, land, and also improving food security. Thank you very much.
A great presentation, Iman. So if anybody has questions, you could use your mic, or you feel free to use the chat. Oh, there's a question here from Gabrielle. How do you calibrate the Armington elasticities for intra-national trade, which turn would be very important, with a very important channel to mitigate the shock impact?
Wonderful question. That's actually another paper. We have a project funded by USDA, and we are working on calibrating or estimating. It's better word. For some part of the world that we have information about that, like the US, we are trying to empirically estimate that, and we have done some sort of calibration in terms of just using historical observations and calibrate that for the US. For the whole world, we don't have a good estimate of everything, but what we do, we are trying to do is using the observation and changes in land use and water use, in prices, somehow calibrate the parameters, all the parameters of the model, not only the Armington elasticity. But yeah, that's an excellent question. Very important. It's a work in progress.
All right. Our next question would be from Angelo. May you elaborate a bit about simple G? Does it represent livestock, forestry sector, pasture, and forest areas? Thanks for the question.
I'm sorry, I did not talk in more detail about simple G, but so simple G is a partial equilibrium model. Some of the information is taken from GTAP. So imagine that you take out the crop productions from GTAP and aggregate them together. That's first. And then we have a livestock sector, and we have processed food sector, and everything else is aggregated together. So why it's partial equilibrium? Because we do not connect the labor income and capital income to demand directly. So in agriculture, we have graded version of agriculture, but for food processing and for non-land production, it's just regional level information. So what you will see is a very simplified version of GTAP. You have the cost structure. You know that the share of labor, the share of labor is another project within this one, but share of, for example, nitrogen fertilizer, land, irrigation, surface water, and groundwater. And these are the information that we have. We somehow downscale that to the cell level using different information. The important part for simple G is that we have grid cell specific elasticities for supply of land, supply of water, groundwater, and surface water, transformation elasticity for allocating land between irrigated and rainfed, which is very important. For different versions, we have different other elasticities too. But so the point is that we consider national level information as well as grid cell level information. All the grid cells within a region are aggregated in one market. So they are competing to produce crops, and they are competing for non-land inputs. At each grid cell, the competition is only for water and land, and in one version, a little bit of labor. Is that enough, or do you have a specific question? Okay.
So I think there's one more question from Justin. Could you share more information on how the gridded elasticities were parameterized in simple G?
Okay, yeah, that's also another great question. So we have different versions of simple G. We have simple G global. This is simple G global with around 2 million grid cells. We have simple G US, which is around 75,000 grid cells. The rest of the world, China is one aggregate unit, for example. US and sorry, not US. India is combined with other countries for South Asia. So for simple G US, we have great details regarding land supply, for example. we estimated that empirically. For water supply, we estimated that empirically. For many parameters in simple GUS, we estimated them empirically. For global simple G, what we use, we don't have enough information to do great work in terms of econometrics or statistical estimation. What we do, we calibrate them using other information. For example, if you want to have land supply elasticity for the regions that we don't have information for each grid cell, we consider different variables like the suitability for agricultural production. There are informations regarding that. These are all satellite map and gridded information, as well as how much of the land is currently cultivated. So if you have 99% of the land already cultivated, it's not easy to increase that. So there are different informations for each grid cell that helps us to find functional form and transform that to supply elasticity for land. For water, we do consider the information regarding available groundwater, available surface water, as well as water table for groundwater. So they will give us some sort of a schedule for cost of extraction of groundwater and surface water. For non-land supply elasticity, we have a version that provides a grid cell a specific non-land supply elasticity. And for that, for example, look at Africa or some other countries that have farms far away from urban centers. So we take information from travel time or market access to consider supply elasticity. So there are many informations out there that can be used. Some of them requires empirical estimations, and we do calibrate a lot of elasticities for global model.
All right, and then I think we have time for one last question from Angelo again. About the results on the global drivers, the impacts from water stress does not show up in any bars in the graph. Is there any reason for that? Can you elaborate on that a bit?
Yes, yeah, thank you very much. I forgot to tell you this. So, as I showed you, the water stress map was not a mega drought. So it was stress on groundwater and surface water. And for the 2015 and 2016 year that we have shown that, it was not a huge shock for that specific year. And that's why you don't see that in any of the tables. Actually, it is only for one region, if I want to be specific. For South Asia, for India, it is important, it shows up. Another part is that there is a possibility to save water a little bit. So for a lot of different parts of the world, the irrigation efficiency is low. So you can have a better management, at least for the short term. And there is a substitution between water and irrigation equipment, as well as land. So you can do a little bit of deficit irrigation. That means you apply a little bit less water to the same amount of land. You reduce yield a little bit, but you still don't kill the plant. So that's why for this specific example, you don't see it. But in other examples, we have done other watersheds, and you see huge impacts.
Okay, I think we have. I think we don't have very extended in time. So I'd like to thank everybody for attending this session, and thanks everybody for our presenters. And yeah, I hope that you enjoy the rest of the conference. Thanks again, everybody. Bye-bye.
Thank you.